Hello everyone, welcome to a new lecture series on data-driven model predictive control. Model predictive control or MPC is a modern control approach which uses a model of the system to predict the future behavior and to compute the control input that optimizes the predicted behavior. In data-driven MPC, we use the data to either identify a model for MPC or to directly compute the MPC control input. This lecture series discusses the different algorithms in data-driven linear and nonlinear MPC, which focuses on their basic concepts and also the numerical implementation in MATLAB. In this first lecture, we give a brief introduction to data-driven MPC, which is then followed by a discussion on the preliminary concepts from modern control theory.
Here is the overview of this lecture. We will be starting with a brief introduction to data-driven MPC, which is then followed by discussing the preliminary concepts from linear and nonlinear systems and also optimization theory. In science and engineering, mathematical models are commonly used for solving real-world problems. In general, a mathematical model describes a system or a problem of interest using mathematical equations. These mathematical equations describes the relationships between the variables of interest in the problem and helps us to understand the problem in a better way. These relationships can be either time-independent relationships, which leads to a static model, or it can be a time-dependent relationships, which leads to dynamic models. In static model, all the variables in the model are defined at the same time as shown in this example, where the current output yk depends on the current input uk. Whereas in the case of dynamic models, the current output can depend on the past output and inputs as shown in this example, where the current output yk depends on the past output yk minus 1 and the past input uk minus 1, and it can also depends on the previous outputs like yk minus 2, uk minus 2 and so on. In this lecture series, we are only focusing on dynamic models which are normally used in control systems. In general, dynamic models can be either represented in continuous time as a differential equation or in discrete time as a difference equation. And the model predictive control or MPC commonly uses discrete time models. Therefore, in the rest of this lecture series, we will be mostly dealing with the discrete time models. The model predictive control or MPC uses a model of the system to predict the future behavior, and the control input is computed by optimizing the predicted behavior. In general, MPC uses a dynamic model of the system to predict the future behavior, and in conventional MPC, this model is assumed to be known, which is obtained from first principle equations. However, in practice, in the case of large and complex processes, first principle models may not be available and also may not be accurate in most of the cases. This leads to the development of data-driven MPC, in which model extracted from data is used for designing the MPC control law. This data-driven MPC can be considered as an approach evolved from the system identification, which deals with extracting dynamic models from data. And we can consider this data-driven MPC as a combination of system identification and control. The advantages offered by data-driven MPC are, it does not require a first principle model. Data is normally available for most of the practical systems such as industrial processes, and also it leads to adaptive and robust control schemes. Since in the case of data-driven MPC, we can have the option for updating the model online using the past or recent data, which is not available in most of the conventional MPC schemes, since these are based on first principle models. Figure 1 shows a block diagram of the data-driven MPC scheme, which consists of a system block and a data-driven MPC block. The data-driven MPC uses the data, which consists of the control input, the output, and also the reference information to compute the MPC control law. Typically, the data-driven MPC consists of a system identification block as shown here, which uses the input and output data to identify a dynamic model, which is then used by the MPC to compute the control law. And in the initial part of this lecture series, we will be considering this kind of a data-driven MPC scheme, which can also consider as model-based data-driven MPC. And towards the end of this lecture series, we will briefly discuss on model-free control. And in the case of model-free control, the system identification step will not be there, and the control input is directly computed using the data. Based on the type of the model, data-driven MPC schemes can be categorized into two groups, which are the data-driven linear MPC or D-MPC that uses a linear model in the MPC control law, and the data-driven nonlinear MPC or D-MPC, which uses a nonlinear model to solve the MPC problem. In the first half of this lecture series, we will be discussing data-driven linear MPC approaches, which includes realization-based LMPC, prediction error method, subspace predictive control or SPC, and data-enabled predictive control or DeePC. Then in the second half, we focus on data-driven nonlinear MPC, which includes neural network-based methods such as recurrent neural network or RNN, state-space neural network or SSNN, etc. Before moving on to these approaches, we will recall some preliminary concepts from linear and nonlinear systems, which are coming up next. In the case of linear MPC, the predicted behavior of the system will be represented using a linear state space model in discrete time as in equation number 1, where k is the discrete time instant and capital NT is called the number of time instants we will apply the control input to the system, which you can also call as the time horizon. Xk is the state vector at a time instant k, and this set X denotes the constraint set for the state Xk, which can be considered as a subset of the n-dimensional space. Uk is the control input vector at a time instant k, which comes from a constraint set U, which is a subset of the set Rm. Yk is the output vector at a time instant k, which comes from a constraint set Y, which is a subset of Rp. And A, B, C are the system parameters, which are the system metrics, input metrics, and output metrics respectively. And this small letter n is the system order, which is also same as the dimension of the state vector. And this capital N denotes the prediction horizon in the MPC problem. In the case of conventional MPC, we assume the system parameters or these ABC matrices are known, which are then used in the MPC optimization problem. When it comes to data-driven MPC, the main distinction is that the system parameters or these ABC matrices are unknown, and all that we know are consist of the trajectories of this input and output data. That's why we call these MPC schemes as data-driven MPC, where the data is available to us, using which we compute the control law. Now, using the state equation, we can compute the predicted state sequence as in equation 2, where this capital Xk plus 1 contains the predicted state over the next n instance. By using the state equation, we have the state Xk plus 1 will be equal to A Xk plus B Uk, and then Xk plus 2 will be equal to A Xk plus 1 plus B Uk plus 1. And there, if we substitute the expression for Xk plus 1, we will obtain it as A square Xk plus AB Uk plus B Uk plus 1. And then by recursively applying this state equation, we can compute the states for the next n instance. By combining all this vector, we can define the predicted state sequence vector or capital Xk plus 1, which will be equal to Ax Xk plus Bx Uk, where Ax is this matrix and Bx is this matrix. And this equation we can call as the predicted state sequence equation, which play a key role in the case of state-based LMPC schemes. Similarly, we can have the predicted output equation as Yk plus 1 equal to C Xk plus 1, which will be equal to Ca Xk plus Cb Uk. Using this equation, we can compute the predicted output for the next n instance, where we have Yk plus 1 equal to Ca Xk plus Cb Uk. And by recursively applying this equation, we can compute all the output for the next n instance. And all these terms we can combine as the vector capital Yk plus 1, which will be equal to Ay Xk plus By Uk. And this equation will play a key role in the case of output-based LMPC schemes. Next, another important property which we assume in the case of MPC is the controllability of the system. And here we can recall the state equation as in equation number 5. And this controllability can be considered as a property or the ability of the system to drive it from any initial state to any desired state using a finite control input. Without losing any generality, we can consider the desired state to be origin. Therefore, the controllability can be defined as the ability of the system to drive any initial state to origin. And it can be formally defined using the concept of a controllable subspace or CS, which is a set of initial states for which there exists a control input sequence of finite length that can transfer the system from this initial state to origin. And in general, a system is said to be completely controllable if the controllable subspace or CS equal to Rn. It basically means that we can transfer any initial state in the n-dimensional space to the origin. It means the system is completely controllable. Now from the state equation, we can have x1 will be equal to ax0 plus bu0 and x2 will be ax1 plus bu1. And here if we substitute for x1, we can expand it like a square x0 plus abu0 plus bu1. And similarly, we can obtain xk as given here. In the case of controllability, we consider driving the system from any initial state to origin in a finite number of instances, where the number of instances is considered as capital N. Now, if we select capital N is equal to the system order or small letter n, and substituting this k equal to small letter n this equation, we can obtain equation 7, where we have xn will be obtained using this expression. From the definition of controllability, we need to find a controllable sequence that can drive the system to origin. In other words, if we replace this xn with 0, there should exist a controllable sequence. And here, if we substitute xn equal to 0, we obtain a raised to n x0 should be minus of this term, which can be represented as in equation 8, where we have a raised to n x0 obtained as the product of this matrix and this control input sequence. And here this matrix we call as the controllability matrix, which contains B, AB till a raised to n minus 1 B as its columns. And this is a column vector which contains all the control input sequence from time instant 0 till n minus 1. Here we obtained a linear equation which gives a raised to n x0 equal to minus of Cn u0, which can be solved for u0, and the solution can be obtained as an equation number 9. From the linear algebra theory, if this matrix has full row rank, there will be always exist a unique solution for this u0 which satisfies this condition. This basically leads to the criteria for controllability, which says that the system or this AB pair is said to be completely controllable if this controllability matrix or this particular matrix has rank n. Similarly, there is another property of the system which is called observability, which is associated with the output and the states. And the observability can be considered as the ability of the system to extract its initial state from a given input-output data, which basically means if the system is observable, we can able to extract any initial state or any previous state from the input-output data of sufficient length. Now, from the output equation, we have y0 will be c x0. Y1 will be C x1, which is equal to CA x0 plus CB u0, and which we can have go till yn minus 1. All the equation can be compactly represented as in equation 11, where we have y0 till yn minus 1, which we can also call as the vector capital Y0, which will be equal to this matrix into x0 plus this matrix into u0. And here we call this matrix as the observability matrix and denoted by On, which contains C, Ca till Ca raised to n minus 1 as its rows. Here we can prove that the system is observable if we can find this x0 from this input and output data of length n. Now from this equation, we can have On x0 will be equal to y0 minus b0 u0, which we can write as in equation 12. Similar to the controllability case, we can find a unique solution to this equation if the observability matrix is of rank n. And this leads to the definition for the observability, which states the linear system is said to be observable if the observability matrix or On has rank n. Now in the case of linear MPC, we assume the system is controllable and observable. Next, we move on to the definition of a Hankel matrix, which is commonly used in the data-driven MPC. And a Hankel matrix is characterized by constant entries along its ascending skew diagonal. And in this lecture series, we will be defining a Hankel matrix which consists of n by h samples of the vector v as the matrix H, where this capital N denotes the number of row entries of the matrix, and this capital H denotes the number of column entries of this matrix, and this Vk will be the starting element of the matrix. Here we can see that these q diagonal elements are the same, which means this Vk plus 1 will be appearing along this q diagonal, and Vk plus 2 will be appearing along this q diagonal, and so on. Here this first column contains this vectors Vk till Vk plus n minus 1, which we can represent using the vector capital Vk, and the second column we can represent using the vector capital Vk plus 1, and so on. So here this is a data sequence, and this is a shifted sequence by one instant, and thereby it captures the temporal or spatial relationships in the data. Hence it is commonly used in system identification and signal processing. Now in the case of system identification and data-driven MPC, one of the important property is that the input-output data which we are using for identifying the system should be sufficiently rich. It basically means that the data should contain sufficient information which captures the entire dynamics of the system. And we can use the Hankel matrix for defining the richness of the data. And this criteria is known as persistency of excitation criteria, which says that the input sequence of finite length D is said to be persistently exciting with order n. The Hankel matrix, which contains n this row entries, has full row rank, which basically means the rank of this Hankel matrix, which contains this n row entries, should be equal to small letter m into n. Now in the case of data-driven MPC, we assume the input-output data used in the MPC to be sufficiently rich, and in most of the cases we assume this persistency of excitation criteria is satisfied. Next, we move on to discrete time nonlinear systems. And in the case of discrete time nonlinear system, the state and output dynamics will be defined using nonlinear functions. And we can represent it as in equation number 15, where xk is the state vector, uk is the control input vector, and yk is the output vector. F is the state function which maps the current state to the next state under the control action uk, and h is the output function which maps the current state to the output. In the case of nonlinear system, this f and h are considered to be nonlinear function. Here we move on to a definition which is called Lipschitz criteria. And in the case of nonlinear systems, we normally assumes this f and h functions to be Lipschitz, which basically says that there exists some finite constants such that the difference of this function for two different states x1 and x2 is bounded by lf times the norm of this difference between x1 and x2, and similarly for h as well. This criteria says that this functions f and h has finite slope between any two data points x1 and x2, which basically says that there is no sudden jump in this function, or in other words, these functions are sufficiently smooth. And in the case of nonlinear system identification and MPC, we assume the original system to be Lipschitz. Next, we briefly recall the definition of an optimization problem. And in general, an optimization problem can be mathematically represented as in equation number 17, where our objective is to find the optimal value of the decision vector z, which minimizes this cost function defined by f. Here, this set z denotes the constraint set, and this cost function can be a linear function such as C transpose z, and it can also be any nonlinear function. Two of the optimization problems which we are commonly going to encounter in the rest of this lecture series are the quadratic programming problem, or QP, and the nonlinear programming problem, or NLP. In the case of a quadratic programming problem, the cost function will be a quadratic function as shown here, and the constraint sets will be defined using linear inequalities and also linear equalities. And these optimization problems are normally convex optimization problems. Whereas in the case of nonlinear programming problem, the cost function is a nonlinear function of the decision vector z, and the inequality and equality constraints are also nonlinear functions which can be represented as here. In the case of nonlinear MPC, the optimization problem will be normally in the form of a nonlinear programming problem, and in the case of linear MPC, the optimization problem will be in the form of a quadratic programming problem. In the next lecture, we will be giving a brief introduction to conventional MPC, where we represent the output-based and state-based linear MPC optimization problem as a quadratic programming problem as in this equation. That leads us to the end of this lecture. Thanks for watching.